All right, so earlier today we looked at calculating heat, the amount of thermal energy that an object could either lose or gain, because that can happen. And now what we're going to do is look at when two objects interact with each other, and one is hot, not one is cold. And so what we're going to look at is when you're dealing with heat transfer, the amount of energy that is gained is equal to the amount of energy that's lost. Now you'll see that I have a minus sign there. This is a formula I won't use as much. The minus sign is because when you have heat lost, your Q value is negative. And so in terms of the magnitude, the size of the energy that's lost, well, it's going to equal the amount that's gained. Now this is the formula I'm going to more or less use. And because it is, again, following the conservation of energy, because energy is neither lost nor gained, is that the amount of energy that's gained by one object is the amount of energy that's lost by another. And so I have Q gained plus Q lost is equal to 0. Because again, Q gained would be the amount of, it would be a positive number, and yet again, the energy lost would be a negative number. All right, so on that note, I'll get to my first example. Example 1. It says if 200 milliliters of alcohol, which has a C value, specific heat capacity of 2,500, at 20 degrees Celsius is placed in 1 liter glass of liquid that has a specific heat capacity of 4,800, that is at a temperature of 0 degrees, determine the final temperature of the alcohol and the liquid. All right, so again, looking at this alcohol is at 20 degrees, this liquid is at 0 degrees. So I'm going to put down my information here of one object is gaining heat, and the other one is going to lose heat or has lost heat. All right, so the object that is at 0 degrees, or the material or liquid, I should say, that is at 0 degrees is the one that is going to be gaining our heat. All right, so it has a mass of 1 liter. Now again, in terms of switching from liters to kilograms, they are equal. All right, so 1 liter refers to 1 kilogram. This liquid has a heat capacity of 4,800. All right, now the other item that we don't know about, we do know its initial temperature. All right, so when I look at finding the delta T, because that's part of our formula here of finding our amount of heat, Q, the temperature is TF minus your initial temperature. So your final minus your initial will always be your delta T. Now in this case, we actually do know the initial temperature. It is 0 degrees. So TF is going to become, or TF minus TI is going to become TF minus 0. Which in fact is just going to end up being TF. That kind of simplifies things. All right, now the one that is going to lose heat is the alcohol. All right, now its mass is 200 milliliters. Now again, converting that to kilograms, a milliliter is equal to 1 gram. And so I'm going to take this number of 200 milliliters and divide it by 1,000. And so that I end up with 0.2 kilograms. All right, now the C value of this alcohol is 2,500. And again, when I'm looking at the delta T, the change in temperature, I have the final TF minus the initial. Now we know the initial is 20 degrees. All right, so there's my information that I have all written out. Now, again, I don't like using this formula, even though they are the same. I'm going to use Q gained plus Q lost equals 0. All right, which means when I'm finding Q gained, that means I'm going to have to take the mass of the material that gained the heat times the C value of the object that gained the heat times the delta T of that whole situation, plus the Q lost, where I'm going to have the mass of the material that lost the heat, the C specific heat capacity of the material that lost the heat, and then again times the delta T. All right, so now substituting in. So I have my mass gains, and that's why I like to get everything organized here. It is 1. Perfect. That's going to be easy to multiply. The C value is 4,800. And my delta T here is simply actually just the TF. All right, plus, now we get to the Q lost part of it. The mass of the object that lost heat is 0.2. My specific heat capacity is 2,500. And my delta T is TF minus 20. And again, this all equals 0. So again, here's my heat gained. Here's my heat lost. All right, now, what we have here now is one equation with one unknown. So we can solve that. So 1 times 4,800 times TF. Well, that's just going to be 4,800 TF. Now, I've got to simplify this a little bit. 0.2 times 2,500, which is 0.2 times 2,500 is 500. And again, that's going to be times TF minus 20. All right, now, again, to simplify this, I'm going to have to do what I call the rainbow rule here, or as math people would say, the distributive property, although I don't even bother with that because nobody remembers it. All right, so again, simplifying here, we got 4,800 times TF plus, let's see here, 500 times TF, which is just going to be a 500 TF, and then a 500 times a negative 20. So it's going to be minus whatever it is, and we end up with minus 10,000 equals 0. All right, so now collecting like terms. I'm going to put my TF terms together. So I got 4,800 times TF plus 500 times TF. Add those together, it should be 5,300 times TF. Now in the same move, I'm going to make 2 moves here at once. I'm going to move this minus 10,000 over to the other side, so it becomes a positive 10,000. All right, and let's see here. Well, last step, we want to find the final temperature of these two things when they're mixed together. So I'm going to divide both sides here by 5,300. And I end up with, those divide each other out. I'm going to end up with my final temperature here. That was the whole thing. I take 10,000 and divide it by 5,300. I know it's going to be 1 point something. And I end up with, let's see here, do a little math. I get 1.89 degrees Celsius would be the final temperature of our mixture. And there we go. So again, the hard part here is get your values down first and then set up the equation. And then we have to do some math to get it all figured out. All right, so let's try another one of those. Second example. Get rid of that formula because I'm not going to use it. Ooh, I should have got rid of that one. All right, so let's see here. All right, so our second example. Again, I always like to read things first, and then the second time I'll get my values down. So if a 200-gram piece of metal at 350 degrees is placed into 300 milliliters of water that has a specific heat capacity of 4,180, that is at a temperature of 10 degrees to be cooled quickly, the final temperature of the mixture is 33 degrees. Determine the heat capacity of the metal. Okay. All right, so here we go. So we have Q gained and Q lost. So let's go with gained, I guess, here first. And we have lost. Right? So one of them loses, one of them gains. Now it looks like, well, the piece of metal here is at 350, so it's definitely going to be the one losing the heat. So our liquid here, our water, is gaining the heat. And again, the mass, it says, is 300 milliliters. And again, for conversion purposes, milliliters are equal to 1 gram. And so, as I've mentioned many times before, there's 1,000 grams in a kilogram. So we're going to have to divide this number by 1,000, and it's going to be 0.3 kilograms. Again, we're talking about the water here. It has a specific heat capacity of 4,180. Delta T is up next, which again is our final temperature, which in this case looks like it is 33 degrees. Is the final for both of them, obviously, because they're being mixed. And it initially is at a temperature of 10. And so, well, 33 minus 10, I know is going to be 23 degrees Celsius is the difference there. All right, so it gained heat. Now, the next one, the lost heat. All right, so we have, first of all, the metal has a mass of 200 grams. And again, converting that to kilograms, dividing by 1,000, so I get 0.2 kilograms. All right, the specific heat capacity is actually what we're trying to figure out. Okay, so I got a question mark there. Let's see, our delta T, our temperature. This is important not to mix them up. Again, it's your final minus your initial. It says the final here is 33. Minus the initial temperature, this thing was at 350 degrees. And so our delta T is going to be a negative number because, again, it's losing heat. And let's see here. I'm going to have to do a calculator on that one. 33 minus 350 is minus 317 degrees. All right, so now, again, I've got my information down. I've only got one unknown here. All right, so again, I'm going to use my formula here where I have mass gained times the C of the thing that gained times delta T plus same idea here with ML, CL, L's stand for they're losing heat. All right, is equal to 0. All right, so our gains here. The mass, 0.3. Excuse me, the C value, 4,180. And our delta T, we do know it is 23. All right, plus, let's see, the mass of the lost, 0.2. The C, well, that's what we're trying to find out here. So I'll just put a C here. Delta T minus 317. And that is equal to 0. And again, you can see how the law of conservation of energy is going to work here, because when we multiply these three numbers, we're going to get a positive number. When we multiply these three values, we'll get a negative number. And again, because the conservation of energy, we add them together, we're going to get 0, a net 0. All right, so on that note, multiplying 0.3 times 4,108 times 23. What do I end up with here? No way. Okay, I actually got a round number here. 28,842. 28,842. All right, again, for the second part here, when you're doing multiplying, you can do that in any order. And so I'm going to go 0.2 times negative 317. Positive times a negative is going to give me a negative here. And I end up with, let's see here, negative 63.4. And of course, it's times our C value there. And that is equal to 0. All right, well, now we're down to simplifying. And so to solving, so I'm going to get the C term by itself. I'm going to move that over to the other side. So I have 2,842 is equal to 63.4 times C. All right, so my last step here to find my C value, I'm going to divide both sides here by 63.4. All right, so those 63.4s divide each other out. And the specific heat capacity, well, I take my 28,842 and I divide it by 63.4. And let's see here, we get 454.92 would be the specific heat capacity of this metal. And often what can happen in science, not just in this circumstances, is that when we find the specific heat capacity of that particular metal, it allows you to identify that metal. And so we get to part B. It says identify the probable identity of the metal. And again, this is where our formula sheet comes in handy, where I have that table that's on the formula sheet. And so I look for 450. Now these values are all times 10 to the power of 2, which means times by 100. And the closest one, it's not exact, but we'll get to that, would be iron. No, is it iron? Yes, iron is the closest one, because iron is 450. And now the second, or the C part to the question is, why isn't the heat capacity exact? Because iron is 450, this is 454.92. Couple of things. It's maybe not 100% pure iron, which definitely happens often in nature, is that it might be very close to pure, but it's not quite pure. Or in this experiment, maybe heat was lost from the top of the glass. That's another example of why your heat capacity might be a little bit higher. But again, when you're looking at this kind of stuff, your numbers often will not be exact, because that's what really happens in nature when you're looking to maybe identify a material. And so my best guess here is that it would be iron, because it's very, very close. But again, that's what happens when we have two materials and they interact